For molecular formulae, masses, and composition, you've already kind of gotten the hint or the hang of what we're doing so far. All right? So molecular formula. Let me give you a molecular formula. And I'll give you C6H12O6. It's glucose. All right? This is a molecular formula. Now, if I want to figure out how much one of these things weighs, what's the best way to do that? All right, per molecule. Well, I can do actual analysis in the lab and figure out what the weight is. Okay? And then whenever I say molecular weight, this is what we mean. That molecular weight is something that's generally been measured in a laboratory, so we know what that is. But we can get a very good approximation by using something called formula mass. Or the formula weight. And what this is that this is an addition of all the atomic masses that are in the molecular formula. So formula mass is the addition of all masses, of all atomic masses, in a molecular formula. So to get the formula weight, and a lot of times you'll hear me or other people talk about molecular weight, they're almost interchangeable, okay, for the most part. If you get somebody, if you get somebody who works at NIST, National Institute of Standards, what they're going to do is look at you and say, oh no, don't interchange them, that's bad, okay? Then they'll give you an hour lecture on why their job is fascinating and important. They're not wrong, okay? But in the real world, we don't have time to sit there and give the molecular weight of everything. So what we use is the formula mass to get a very close approximation of what the mass is going to be. All right. So to find formula mass, what I'm going to do is I'm going to take the number of atoms, okay, and then multiply it by the atom's molecular weight, by the atomic weight, excuse me. All right, and then add them all together. So this is going to be a sum of all the atoms, or all elements. Okay? So to give you a general idea, I mean, once I draw this, because some people are starting to panic, like, so make sure I do that. Yes, you do have to do this. Just adding things together. Okay? So let's look at this. So I've got 6 carbon. So what I'm going to do is I'm going to get 6 times carbon. Okay? And then I'm going to add that to 12 times hydrogen. And then I'm going to get 6 times oxygen. Okay? And all of those added together is going to be my molecular weight, my formula weight. My formula mass here. Okay? So, what do? Where do we find these numbers? I'll give you a hint. It starts with P and ends with periodic table. Yeah, the periodic table. Each one of these is the atomic mass. So for carbon, I've got 12.011. Okay? For hydrogen, it's 1.0079. And for oxygen, it's 16.00. So now put those into your equation. So I've got 6 times 12.011 plus 12 times 1.0079 plus 6 times 16.00. And this will give us what the formula mass of glucose is going to be. All right? All right, what I get out is when I put this into a calculator, I get 180.16.0 or 0.1608. And what this is this is the mass and AMU of the molecule. All right? Now, when we actually look at these things, and we start doing this in the laboratory, we're going to identify this as grams that we get for every 1 mole of material. The grams for every 1 mole. Now, what is a mole, you say? A mole is a defined amount of atoms inside of a certain a unit. And it was defined by Avogadro. Okay, and Avogadro's number Avogadro's number states that there are 6.022 times 10 to the 23rd atoms in 12 grams of carbon-12. Okay, it's important to designate that it's carbon-12. Okay, and he was able to figure this out, and so as isotopically pure carbon, he figured out this value, okay, and this number became something that we use as kind of a standard. All right, so if you notice in the periodic table, carbon's mass is 12.011 because you got to include the isotopes. That means for all naturally occurring carbon, if I've got a mole of it, if I have 6.022 atoms, or times 10 to the 23rd atoms of carbon that are naturally occurring, the mass is going to be 12.011 grams. Okay, so the same idea is going to be applied to every single atom that we've got. A mole is 6.022 times 10 to the 23rd. It's just a defined unit. You want to look at the atom and you want to say, well, this value that we've got is similar to saying a dozen. If I have a dozen of something, I know I've got 12 of something. If I've got a score of something, I know I've got 20 of something. Okay? If I have a gross of something, it means I've got 144 of something. Yeah? Okay, so the same thing goes on here with the atoms. If I have a mole of something, I'm always going to have this number of atoms. Okay, so what this says is that we can use this as a specifically defined unit and always know what the mass of these particular atoms is going to be. It's a very useful convention for us to be able to react 1-to-1 ratios of carbon to oxygen. Okay, so if I have a mole of carbon monoxide, okay, that means I've got 6.022 times 10 to the 23rd carbons, and I've got 6.022 times 10 to the 23rd oxygens. The same amount, because I've got carbon and oxygen, the same number of atoms inside that molecule. Okay? So if I have a mole of each one of these, right, this is 6.022 times 10 to the 23rd carbons multiplied by 6 of those. Okay? Over here, if I have a mole of oxygen, that's 6.022 times 10 to the 23rd multiplied by 6. Same thing with hydrogen, except multiplied by 12 there. And that's how I get these particular amounts or numbers of atoms in each one of these molecules. But rarely are we really interested in the numbers of molecules so much as what they weigh, because it's easier for us to weigh something than to try to count every single atom inside of a mole. Okay? So when we get molecular formula, the molecular formula allows us to calculate what the formula mass of something's going to be. And this tells us how much in a mole I'm going to have as far as mass goes. It's a very useful thing. Okay? All right. Now I'm going to erase. Okay. So now we're going to move on to percent composition. And what percent composition is it tells us how much oxygen, or it tells us what percentage of everything is inside specific molecules. All right? And remember, this has a relationship to empirical formula. If you read your textbook, you'll be able to see that there's a relationship between empirical formula and percent composition. Because when you blow these things up in an elemental analysis, you're going to get out empirical percent composition, which gives an empirical formula. And from that empirical formula, you should be able to get what the actual molecular formula of something's going to be. It's not something I teach, per se, and I expect you to do mathematically, but it is something that you might run into in a real-life application. So check it out inside of your book if you're curious. So percent composition, how much oxygen is in 1 mole of ethanol? Okay? Now, question 1, what's the number of units? Okay? So I'm going to look at this and I'm going to say I've got 1 mole of ethanol. So I've got 1 mole of C2H6O. So how many moles of oxygen are inside of that? 1 mole of oxygen. All right, so that's easy, right? So now part 2, what's the mass of the oxygen that's inside of it? If I have 1 mole of oxygen, all I have to do is multiply that by the molecular weight. Because notice here my moles cancel out, and that's going to give me 16 grams of oxygen inside that mole of ethanol. All right? Now, using that general idea, or something similar, I'm now going to throw this question at you, and I want you to figure out what the percent composition of ethanol is oxygen. Okay? So what percent of oxygen, or what percent of ethanol is oxygen? Okay, I already know oxygen is 16 grams. So an easy way of looking at this is let's find out what the formula mass of ethanol is, and then divide the oxygen mass by the mass of ethanol. So ethanol, if I calculate this, that's 2 times 12.011. This is 6 times 1.0079. And this is 1 times 16.00. Okay? Now, what do I have from that? And what I would recommend you guys do with this is try to solve this first, and then see if you get the right percent composition before I solve it for you. So go ahead and hit pause, and then hit play when you're ready. All right, and what I get out mathematically is 46.0694. And this is the number of grams that I get for every 1 mole of ethanol. Okay, so another way of saying that is that that's the formula weight of ethanol. So the percent of ethanol is oxygen. What I do is I take the mass of oxygen and then divide it by 46.0694 and multiply it by 100%. Okay? That's the mass of oxygen. That's the mass of ethanol per mole. And then what I'm going to get is, let's see, 16 divided by that. I get 34.73%. So that's the percent composition that is ethanol, or that is oxygen, in a sample of ethanol. All right? When you burn any sample per mole, you'll be able to figure out that every time 34.73% of the ethanol that's being burned is just oxygen weight. Okay? If I did that with carbon, what I'd do is I'd take 24 divided by this value and get a larger value, and the same over here with hydrogen. And that's how I get percent compositions there. All right, so the final problem that I want you guys to work on for this is I want you to take this value of sodium carbonate, which is 18.73 grams, and I want you to work this out, and I want you to figure out what the value, or what the number of moles of sodium carbonate I've got with this mass, and then find the percent composition of sodium. Okay? Try to work that out, and hit pause, work this out, and then see how I work it, and see if you're close, and hopefully you've got the right answer. All right, now here's the solution for both of these parts. And what I did is I took the mass that I started with, okay, and I divided it by the molecular weight. And I got this value by adding up the 2 sodiums, the carbon, and the 3 oxygens together to get the molecular weight of sodium carbonate. And the unit value that I got with this is 1.1671 moles. Okay? Now there's one thing that's important here. I want to see if you can spot it. But I want to make sure that my significant figures are correct. Now, are my significant figures correct? I've got 1 sig fig here, but that's a definition. So that's an infinite number of sig figs. But what about that? That's a calculated value. So I've got 5 sig figs here. How many sig figs do I have there? 4. Now, how many sig figs do I have in my answer? 5. So make sure that your sig figs are correct. So I just dropped that 1 off. So I've got 0.1767 moles. Over here, on the bottom here, to find percent composition, I take 2 times the mass of sodium, because that's what I'm trying to find is the composition of sodium. This is the atomic mass of sodium. Okay, atomic mass of sodium is 22.99. Multiply that by 2, and then divide by the overall molecular weight, and what I get is that percent composition. Do I have the correct number of sig figs there? Yes, I do. All right, good. So work on some problems that are associated with this and to get better at this, because I will say that this type of calculation you run into in all levels of chemistry. By the time you get out of general chemistry, you should have this down pat.